So I'm glad to introduce Sergio Chaves from University of Rochester, who's going to talk about remarks on the combinatorial topology of moment-angle complexes.
All right, so thank you, Alex, for the introduction, and thank you for the organizer for the opportunity to present some of my work here. So before getting into the remarks on my talk, I would like that everybody thank the organizers for this amazing workshop and the Fields Institute for hosting us. So please give a big applause to Tony, Stephen, Graham, Angeline. Yes. Yes. Yes, I'm very bad at short memory things, so I will need your help in this talk to fill in some gaps in my talk, as you just see. So the title of my talk, is Remarks on Combinatorial Topology of Moment-Angle Complexes. And you might agree with me that this is a very vague title, because you know how combinatorics is connected to topology when we explore polyhedral products. So this could have been the title of any of the talks during the workshop, right? But it turns out that there are certain type of combinatorics that we can do with moment angle complexes and polyhedral products when we ground things down and we apply all these big theorems that we have here. So this is going to pick up on some directions of the late Fred Cohen work at the University of Rochester. So I'm going to pick up from some of Fred's latest PhD students, and they explore your typical discrete math problem, and now using polyhedral products. So it might come a day when we need to teach undergrad students in discrete math polyhedral products, right? So this talk is going to be, as I said, very grounded, very on the basic level, and there won't be very big surprising result. It's mostly an acknowledge and celebration of this talk, and I think this is a very nice way of closing the workshop with things that are very grounded, and we see the applications with very specific situations of all these big theorems. So as I said, this is going to start very basic. So topology as a subject starts with counting, and the earliest topological invariant is due to Euler's, thanks to his famous polyhedral formula. So if we take a polyhedral model of the sphere and we count the number of vertices, subtract the number of edges, and add the number of faces, we definitely know what we get, right? So can someone help me with this number here? 3, right. Very good. So we are all topologists here. So we used to run things first and then fix them. So we know that definitely this is true. And this is kind of funny because when a non-mathematician person or an undergrad student asks me what kind of research you do when you do topology, I usually bring something out relating this formula. This is something that is excessive. And now that I'm in front of experts on topology and polyhedral products, I'm also bringing the same formula to explain things out. And more generally, we are going to use this extension that we all recognize for an oriented surface of genus G. The Euler characteristic ends up being 2 minus 2G, right? So as I said, this is going to be a very combinatorial talk. Combinatorial in the sense that we are going to actually count things. So we can also recognize the early explorations on polyhedral products, everything that has brought us to this day. So the earliest exploration come from the Davis-Januszkiewicz construction, and later generalized to the moment angle complexes by Panov and Buxtehude. But there are even earlier records that we can relate to our modern construction of polyhedral products that are the Coxeter surfaces. That this formula comes from the 30s, while this work starts in the 90s, 2000s. So if we take the simplicial complex that comes from the boundary of the n-gon, then the polyhedral product, or the real moment angle complex, also called, when we take interval and 2 points ends up being a surface. And as I said, I need the help from the polyhedral people here. We know what this genus is. Does anyone remember the formula for the genus of the Coxeter's surface?
It's a hard to remember formula.
Right?
And we are all old.
Exactly. I'm getting there, Tony, so this is maybe why I need the help of the younger researchers.
Martin knows what it is.
Martin, do you know it? I think it's close enough, right? I'm not sure if this is correct. I don't also know the formula yet. But or there is a +1, exactly. Very good. So we are fixing things up together, very nice. Right. So as a good mathematician, we never know any formula, right? But we know how to derive this formula. So I'm going to teach everybody, or maybe all together we can just count this number, just using Euler's formula for fun, right? So how this works? So we have Kn, the simplicial complex, which is the boundary of the n-gon for n greater or equal than 3. And the polyhedral product I'm going to call Xn is embedded into the n-dimensional hypercube. And by the definition of how we construct polyhedral products is the union of these sigma I components, but sigma I is one of the edges of the polygon. And it turns out that this comes to be the product of two disks in two adjacent components inside of this hypercube, where the others are just S0 or 2 points. These are the components. So we can see N3. So again, this is a very grounded construction of how things work with concrete examples. So if we do the polyhedral product construction over the triangle, we see the three-dimensional hypercube, the regular solid cube. And the three components of the polyhedral product are these 6 square faces, top and bottom, side, front, and back. And if we take the union, we just recover the boundary of the cube, which is homotopically equivalent or homeomorphic to a sphere, right? And I also borrowing this picture from Martin, Tony, and Fred's paper that they also borrowed from Trevison's thesis. That now, if we do the polyhedral product construction over the boundary of the square, then we have the union of 4 components, each being 4 squares. So this is how we see the torus inside the 4-dimensional hypercube. It's a very nice picture, and I think it's nice to see it here again. But in short, we see that Xn has a polyhedral model, and we can count its number of vertices, its number of edges, and its number of faces. So it's a very simple problem that you can propose to your discrete math students. Count how many vertices, 2 to the n, how many edges, so you fix one interval and the other are free, so n minus 1. And the number of faces, you fix 2 adjacent positions, so you have n possibilities for that, and then you have 2 to the n minus 2 points, so you have that number of faces. And if we just compute what the Euler characteristic is, we do the sum, we use that is 2 minus 2g, and then we recover that formula, right? So even if you don't remember now the formula, I hope that you know how to get the formula.
That's an embedding in R4.
Right. Yes, it embedded in R. This is the hypercube in R. Exactly. All right, so I hope that whenever you get asked this type of genus formula, you get to use your basic combinatorics and your basic topology to derive this type of formula. So what is another direction that we can take? This is something that hasn't been explored much in polyhedral products. Usually when we have the real moment angle complex or the complex moment angle complex, we look to either the torus action or the Z2 action to the n in the space. But it hasn't been done much about the simplicial automorphism group of your ground simplicial complex. So the automorphism group acts in the simplicial complex, and it extends to an action to the polyhedral product. So in our case of interest of Kn, the automorphism group of the n-gon is the dihedral group, but I'm going to make things easier just to focus on the cyclic part of this group, right? And what this action is going to do is going to permute these components of the polyhedral group. So if we go back to the previous slide, so in D3, the action of C3 is going to permute one of these two squared to the next, is the cyclic permutation, and same for the action of C4 in the torus. It's going to permute these squares cyclically one into the other. So this is an action that contains two fixed points. And for the case of n equals 3, this coincides with just the rotation action of the sphere by 120 degrees. Right? So basically what you can do is you can put the square not lying on its face, just lying on a vertex. So you have the two fixed vertices, and the action is just rotating 2 pi over 3 degrees. So it's not hard to see this connection. These are the two fixed points that correspond to the two vertices, the two corners of the cube. And the action on the torus is a bit harder now to visualize, but it turns out that this action coincides with the usual square identification construction of the torus, where we just do the pi over 4 rotation on the torus, right? And the fixed points are the corner point and the center point. Remember, we are constructing the torus with this 16 square tessellation. And it turns out that we can also do the same construction in the polygonal model of the torus. This is the polyhedral model of the torus coming for the polyhedral product. And on the right side, we see the polygonal model that we learned in a first class in algebraic topology. But it turns out that it contains the same numbers of square edges and vertices. The action not only acts, it's not only homomorphic, it's a simplicial action between these two models. And what is nice about the action on the right-hand side is that we can also identify what the quotient space is. So in this case, the quotient space will be just induced by looking at this fundamental region. So this will be the quotient, and the identification that we see are here in the lower left corner of the screen. And it turns out to be a sphere, right? So if we count also combinatorially this polyhedral model of the quotient space, we just recover also the usual Euler's characteristic formula for a sphere, right? So however, when things go beyond n equals 4, so for n5 and beyond, things are way harder to visualize. So one proposal is try to see if we can construct an action that is compatible with the usual 2D polygonal model of the surface. So when x is 5, if we use the formula we just recovered at the start of this lecture, the genus is going to give us 5. And if we count the number of vertices, edges, and faces, are these numbers that we see on the screen. And if we want to connect with the polygonal model that we learned in algebraic topology to construct surfaces of any genus, there is an identification on the 20-gon that allows to construct such surface. So this is a very geometric question, a very grounded geometric question is, are you able to draw a tessellation of the 20-gon that construct this surface of genus 5 that is compatible with this polyhedral bond? So you need to use 40 squares, 80 edges, and 32 vertices that somehow recovers nicely the action. So this is a very vague and open question, but maybe if you want to do something on basic geometry, play around and try to see if we can see this 2D tessellation of at least n equals 5, that maybe we can generalize to any surface.
Should mention how easy.
Yes, I'm going to mention, he's going to come up later. Yes. So this work relates back to Al Raisi, Fred's student of, I think 10 years ago. He did all this, explore all this work. Okay? So we have a theorem of Al Raisi that allows to really identify what this quotient space is. So he proved that the quotient space of the real moment angle complex over the n-gon quotient by the action of Cn is an orientable surface, and the map is a branch cover. So then we can use, or he used the Riemann-Hurwitz formula to recover what the genus is.
The action is not free.
The action is not free. There are points where there are fixed points, but there are also points where non-trivial isotropy groups. So this is why we see these different isotropy groups that are going to show up here. This is the count that we are going to make. And we see how this relates to other counts in discrete math. So this count that appears in counting or determining this genus, basically we need to fit in this part, because this is given by Coxeter's formula. This is what we are trying to figure out what the genus is. So we need to make that count. So we need to get our hands dirty and make the basic count in discrete math. So this problem can be translated to counting two-color necklaces. So this is a very old problem. So the problem is you have n bits of two colors, black and white, and how many necklaces can you construct? Necklaces are equivalent after rotation. So for n equals 3, there are only 4 classes. And for each class, we are going to associate a binary number that is written in the next line. So we are going to write a 0 if the bit is white and a 1 if the bit is black. So we have the 4 representative, and below we have their orbits, right? And here at the bottom of the screen, you see what's the stabilizer group or the isotropy group of each class. So it's going to be C3, the identity C3, and the identity in each of those cases. If we do it with 4, then these are the 6 classes, and there are points where the isotropy group is neither the full group or trivial, so it can be any subgroup in between, or any subgroup of Cn in general. That depends on how the structure of the word, the structure of the necklace is going to be. So then we need to make the following count. So we need to count the primitive words. So a word is going to be primitive in 2 to the n, in the sequences of zeros and 1, if its orbit is of maximal size and is the minimal work. So just some representative for these spatial works. So here we see that these are the 3 primitive words in 2 to the 4. I'm not counting the C2 because its orbit is just of size 2. So I want those of maximal size orbit. So as I said, this is a very old problem. So the count comes all the way back to Moreau in the 1872. That is basically an application of what we call today Mobius inversion. So what we have here is a very basic count. Each word is either in the orbit of a primitive word or in the orbit of a primitive word of lesser side, where the side divides n, right? So this basically is generated by this primitive word, 0, 1. And this is generated by just 0 and 1. So we make the count over all divisors. So this is why we have this Moreau's formula. And then we get Mobius inversion to get what the value for m to the n is. So then we can recover the genus formula for this orbit surface. So we make this count that is what we need in the Riemann-Hurwitz formula. So this is going to be 1 word for every primitive necklace or primitive word. So there is going to be such number of repetitions of points with orbit size nd, right? So the size is, or the group is C and D if and only if is coming from a primitive word, or the concatenation of a primitive word of length D. So then we compute that. This is again 2 to the n, the formula that we saw in the previous slide. And this sum just counts the number of the total number of two-color necklaces with n bits, right? So this number here that I'm going to call Pn. So any questions so far in the combinatorics appearing here in these formulas? So then we can recover the genus of this quotient space as the total number of necklaces minus 2 to the n minus 1. And using again that this genus is 2 minus 2g, we recover this formula for the genus of such a surface, right? So again, this is an application of Al-Rais's work and a very known result about complex surfaces. Right, and here this is just a verification, and if we apply for n equals 4, the torus, we see a surface of genus 0, which corresponds to the sphere, this conic sphere that we saw in previous slides. So we can make another count by bringing the action now on the simplicial, the action of Cn on the simplicial complex that extrapolates to the action into the topology, or in this case, the cohomology of the corresponding real moment angle complex. So we all have seen this formula plenty of times during this workshop, the BBCG stable decomposition, but it turns out that one can choose the function here, the homotopy equivalence, to be equivariant under the action of this automorphism group. In the right-hand side, the action is just an action on the set of faces or the set of indices. And when we take the real moment angle complex, the formula just reduces to the double suspension of the geometric realization, formula that also we saw in Lewis's talk. But in our case, this geometric realization is either a sphere, when you take the full subcomplex, 1 through n, or a discrete set of points. And in general, this is the formula that we are going to see. So we're going to make this count from two different perspectives. So we have one count coming from the genus formula, but there is also another count that is going to relate the genus with necklaces as well. So we are going to make the following identification. So for any sequence in the set of vertices, I think this should be M. We are going to associate a word again, whether the vertex is in the sequence or not. So in this case, we have 1, 2, 3. This is my sequence that is not in the complex. And I'm going to associate the word 1, 0, 1, 1, 0. Because we see 1, 3, 4 as vertices of the sequence, and 2 and 5 are missing. And here we have another 1, 2, 3, 4. So this is the face or the sequence that we see. So we associate the word 1, 1, 1, 0. And this sequence is going to induce a non-trivial class in the first homology, because it is homotopy equivalent to 2 points, and its suspension is S1, while the sequence below it is homotopy equivalent just to a point, so it doesn't induce a non-trivial sequence in H1 of the space. So we can generalize this count to count how many change of colors, or what we call color gaps, there are in the necklace. So from here we see there are 2 changes of color. So from black to white, then again another black to white change. And here there is only 1 change of color. So this number of changes of color that we see in the necklace is going to tell us how many generators is going to induce this sequence into the first homology or the first cohomology of the real moment angle complex. So we call this the gap of a word. So it's the number of times that one zero appears in cyclic rotation of the word. And again, remember, this counts just the number of color changes that we see in the necklace. So if we take K6 and this sequence 1, 3, 5 that corresponds to this word, then the gap is going to be 3. And we have this very simple remark. Then for any word, its geometric realization is going to consist of the gap minus one number of points, and therefore its suspension is going to be the wedge of the gap of the word minus one circles. So every word is going to induce this number of generators in H1 of the real moment angle complex. So therefore the rank of H1 is going to be the sum of all these gap numbers minus one for every word that is different from the word 0 and the word 1, the empty and the full sequence word, because they generate the 0th and the 2 cohomology of the space. So we just take all other words different from the sequence of zeros and sequence of 1. So we have then this count. So it turns out that this count, when we add the number of gaps across all the words, so I'm going to call this number G of n, this number has some applications also from certain people that do computer science. They call them these Linden words, and they count some palindromic properties of such sequences. So computing these kind of numbers can be of interest to people in other areas. And if you compute this number using a computer and you do it by brute force, this grows exponentially. So it's a very hard number just to produce by doing the hands-on counting, the brute force counting of count all words, count the gap of each word with a computer. This explodes beyond 7. Beyond 7, this number is hard to compute. Right? It takes the computer a lot of time to do such a calculation. So it would be very nice to have like an actual non-recursive formula that computes this type of gaps. So we're going to combine then with what we know from topology. So on the one hand, using the BBCG decomposition, the rank of H1 is the total gap minus 2n plus 2, what we see at the top of the screen, which corresponds to twice the genus of the space. And we combine with Coxeter's formula to get a very nice formula for the total gap across all binary words of length n. It's going to be n to the n minus 2. All right, so we see that this formula also appears if you compute directly using the computer, that this is the pattern that is going to be followed, but this produces an actual proof of such identity. And as we have an action of a group, we can, of a finite group in this case, we can also bring theory from group theory, group cohomology, and how this relates to other countings that we are going to see here. So this is a theorem from group cohomology. So if we have a module, a ZG module, that is the sum of Z modules, where the action of G on this n module is transitive, so it permutes elements across this direct sum. So this is going to be just an induced module. This is a very classical result on group cohomology. And as a consequence, we have that the first cohomology of Xn, so it's going to be Xn, is going to be isomorphic to a direct sum of induced modules. This is going to be useful to compute group cohomology later. So what I want to do now is to describe the ZCN modular structure of the first cohomology of the real moment angle complex. So if we take the example of the torus, so we don't need all this machinery because remember the action coincides with just the rotation of the square. So we know that the action sends alpha to beta and beta to negative alpha. That's pretty simple to see. But if we use all this machinery of using sequences, looking at the word, and then looking at the generator, we see that the sequence 1, 3 under the action is sent to the sequence 2, 4, and the sequence 2, 4 is sent to 3, 1. That is the inverse of the first sequence. So we can also see combinatorially this geometric action, what happens on the generators according to the BBCG decomposition that sends alpha to beta and beta to negative alpha. So it decomposes as the sum of two Z modules, and is going to end up being the induced action of the sign representation of Z2 on Z. So when n equals 5, and actually when we have any prime number, things are going to be a bit easier because we're going just to see full orbits. So for example, 1, 3, so if we take this sequence, no, my bad. This sequence 1, 3, and then we see its orbits, so the gap is 2, so it induces one generator Z, and it produces a full orbit of size 5. So the representation is going to be a regular representation of Z5 on Z. So we have another word, 1, 3, 4, and these are going to produce the 10 generators of the, remember, this is a genus, surface of genus 5, so there are 10 generators in the first cohomology, and they are going to split as two regular representations of C5 in this manner. And finally, things are interesting when your n is not prime, because there are going to be tons of different situations. So firstly, we have the regular representations. And actually, this comes from primitive words. So the fact that the representation is going to be a regular representation comes from the fact that the word is going to be a primitive word, that the full orbit is of maximal size. Things are a bit messy when this is not a full primitive word with the concatenation of another word. So in this case, if we take 1, 4, this word in 2 to the 6, then it's going to correspond to the sum of just 3 objects. So one corresponding to 1, 4, 2, 5, and 3, 6. And the action is going, in this summand, on the first summand, what it's going to do is going to flip signs. So the action of sigma to the 3, the generator of the group to the cube, is going just to flip signs. And we see that this is the sign representation. For other words, this last word is very interesting because now this is the first word that we have an example of gap being greater than 3. So now each one is going to induce, so there are only 2 elements in that orbit, 1, 3, 5, and 2, 4, 6. But because the gap is 3, remember, this is going to induce the wedge of the gap minus 1 sphere. So the sequence 1, 3, 5 is going to induce 2 generators now in the first cohomology of the real moment angle complex. So then we have an action, transitive action in the sum of 2 copies of Z2. And if we just restrict the action to the square, it's going to do the following. So these are the 2 generators that we see, 1, 3, and 5. So the first generator goes from 1 to 3, and the second goes from 3 to 5. So if we apply the action that sends 1 to 3, 3 to 5, and 5 to 1, then the generator alpha that goes from 1 to 3 after 2 rotation goes to alpha square, goes to 3 to 5. But the generator alpha square now goes from 5 to 1. And if you want to go from 5 to 1 using alpha 1 and alpha 2, you need to do negative 1, alpha 1 minus negative 1, alpha 2. So this is going to induce the following representation. So it's going to induce this matrix. So the first generator goes to the second, and the second goes to the subtraction of the next, or the negative of the sum of the other 2 generators. So it's going to induce this representation, the representation of C3 on Z2 squared induced by this rho W representation. What we want to actually count is how many of each type there are. So as I said, the number of regular representations are going to be given by the primitive word of maximal size, while these induced representations are going to appear by primitive words of lesser size. And this is what is actually going to produce torsion on the group cohomology of H1, sorry, the group cohomology of Cn with coefficients in this module. So this theorem is due to another Fred student, Schumann Das, that basically he described the full Z Cn modular structure of the first cohomology of the real moment angle complex as the sum of induced modules. But basically what we are interested here is in the zeroth cohomology. So remember, this is the zeroth cohomology from group cohomology with coefficients in H1. So this corresponds to the fixed point. So it's going, just using Shapiro's lemma in group cohomology, you see that this is going to be a sum of free modules plus a sum of torsion modules, where the free modules come from the regular representation. So this is the number of regular representations in the modular structure of H1. And just because this is related to the number of gaps, remember, each free module comes from a primitive word. So I'm going to call this the Moreau gap, the sum of all gaps across the primitive words of length n. So the rank is going to come by this sum, the sum across all the Moreau gaps of primitive words minus the number of primitive words. And if we combine this with the genus formula, because the action is simplicial, so remember this translates into the first cohomology of Cn with coefficients in, sorry, the zeroth cohomology with coefficients in Xn. And because the action is simplicial, this is going to coincide with the first cohomology of the orbit space, right? Up to torsion. So maybe after taking a field of characteristic 0, we are just going to make the focus on this count. The sum, this free part is going to be the same, and this gives a count to the total gap of primitive words of length up to n, right? So this shows that we can just ground things down and use very specific examples of polyhedral products and moment angle complexes to derive very nice formulas or combinatorial formulas in a very basic level. So what is the next step? Actually, I'm going to the end of the talk, but the next step is to look now at the moment angle complex. So what happens when you do similar construction, not to the real moment angle complex, but to the moment angle complex, to D1, sorry, D2 is 1. And we are going to see similar behavior as we see in the binomial formula. So in the binomial formula, you know 2 to the n is equal to the sum of the binomial coefficients. And what is going to happen is the first cohomology of the real moment angle complex is going to scatter in the complex moment angle complex across all cohomologies between 1 and n minus 2, because it's going to be, it's well determined what the moment angle complex D2 is 1 Kn is. So this is well determined what it is. It's a connected sum of spheres of different dimensions. But these gaps are going to scatter across all these dimensions. So we can also have nice formulas. Let's say that you want to count the number of necklaces with a determined fixed number of black beads. So you have 10 beads and you want to count how many can you form with 6 and how many gaps there will be just looking at using exactly 6 black beads. is going to be captured by now the combinatorial seen from the moment angle complex. So using what this space is, this space was already calculated tons of times. What his homomorphism type is, as I said, is connected sum of products of spheres of different dimensions. And we connect combinatorially with this necklace problem and gap numbers. We can also derive very nice formulas for some of these number theory and discrete math problems. So another direction that this can take is maybe not take up Kn, maybe change your base simplicial complex, maybe take another very interesting simplicial complex. So one of the actual proposals that Doug Ravenel was trying to see in this is what happens if you take maybe Platonic solids or Archimedean solids? Are there any combinatorial formulas that we can see from the topology to actual discrete math problems? So this opens like a new direction that we can take polyhedral products, is to maybe solve nice counting problems or recover some other formulas that are already known. All right, I think that's a good place to stop. So thank you all for your attention.